the phone without Apple providing the update, and then a Cambridge University researcher last summer did it using $100 worth of equipment off of eBay.
And actually, there's an interesting twist. The rumors are that the Israeli company helped the FBI extract the information from the phone, and by doing so, it became a prime target. Actually, the Israeli company was hacked by hackers, and much of its tools had been publicly released on the net. So they very careful in openly hacking the FBI or targeting targets. So I think I have a solution to this whole debate. I was calling it Trump encryption. It keeps all of your information, the real information, secure, and is a backdoor output alternative facts.
You mean say facts of RSA numbers?
Or the zero-knowledge scheme, I didn't wait. Well, serious, the new U.S. Attorney General Jeff Sessions was quoted a little while ago saying, I'm going to quote him, it's critical to national security and criminal investigators to be able to overcome encryption. Do you have any idea what that means from a technical perspective and maybe implications for policy over the next 4 years? So overcoming encryption, to me, is a backdoor.
But there are many other ways to get around encryption than the backdoor, and I'm not finding, the work I'm doing in Washington, I'm not finding that opinion is necessarily supported by other people in the government, whether in Congress. I don't know if you want to talk about the House Working Group.
Yeah, the report that came out in December was a very interesting report. It was a joint report. It was a bipartisan report. It was joint between the Judiciary Committee and the Energy and the Commerce Committee. And the four conclusions which I thought worth reviewing. First, which I think is the most important one, is listed first. Any measure that weakens encryption works against the national interest. And I guess it's a strong conclusion. I think that encryption is a tool that is exerts strength against the national interest. It's one of the processes there. Number two, encryption technology is a global technology. It's highly increasingly available around the world. So that's again possible to control the secure encryption. That's the effect that I found slow-handed. And third one is the market of space, because there's no one-size-fits-all solution. There's a variety of stakeholders here. There's different requirements. You can't expect it on approach. It's going to work everywhere. The last one says that Congress should encourage cooperation between technology companies and law enforcement. So I think it's a well-written report worth reading, and the conclusions are in the right direction. He said, I'm struggling to force American companies to take those examples that initially the business. And they're not going to the world. There are other companies in Europe and Israel and in the Far East. So the ethical setting is critical. So our secretary was from a few weeks ago, John Brown, and he said that U.S. companies dominate the international market, and there was a theoretical ability of foreign companies to have those encryption capabilities. I don't know if you having talked about that. He probably didn't know that the AES was imported. Can you remind me who invented AES? It was through Belgian researchers. Can you remind me who invented Shafri? Can you remind me who invented threshold analysis? Israelis? Can you remind me who invented fingertip analysis? Japanese researcher? I can go on and on. It's an international game. It's not, it may be strongly influenced by the US, but it is not uniquely American. And I can assure you that any one of my students will be capable of writing good crypto code. So Apple and Google have announced that they're using differential privacy to help protect user data. Can you explain what that is and its significance? Okay, well, yeah, I think you're right. So differential privacy is mess up the data just a little bit, but mess it up enough that it's only a little bit so it's still useful. It doesn't always work, but you hide the data, you hide the information in such a way that if somebody is in the group or not in the group, you can possibly tell because you touch the data a little bit. Let me give you a simple and nice example. It's out of some work done at Google. You want to know whether somebody is doing a particular thing, whether they answer yes or no on a query. And so what you do is you toss a coin. If the coin turns up heads, then the answer is yes, regardless of what the user is doing. If the coin turns up no, then the answer is whatever the user has said, either yes or no. Now, of course, that gives away if the user has said no. So you can do it twice. You can toss the coin twice. And the first time the answer is always yes, and the second time the answer is always no. And so if you get an answer to the right person on stage, if you get a tail on a tail, then I get the correct answer. Otherwise, you don't. The point is, you're smushing the data enough that in that particular case, it's still useful to whoever's trying to collect the data, but it hides the information about any particular user. And that particular system called Rapport, R-A-P-P-O-R, is used to clone for certain kinds of data. The GPU Technology Conference was born by the invention of CUDA and the invention of GPU computing. And we're really inspired by the fact that graphics is more than just a pipeline. Graphics is computational, and visual computing is broader than just making pictures. You start with physical simulations, parallel computation, and a lot of math and a lot of understanding. And you build the pictures, and you build solutions along with the pictures. GPU computing has experienced exponential growth. CUDA is the realization of two kinds of computer processors working together. The CPU is a high-speed, serial, single-threaded processor, low latency, can process a small amount of information very quickly. The GPU is a highly parallel, high-throughput processor, many threads, many pieces of data, lots of things happening at the same time. So the marriage of these two kinds of processors, enabled by the CUDA programming environment, allows us to achieve many exciting and interesting things. Japan has been growing and evolving. The first GTC Japan in 2010 had just under 500 attendees. Today, I think we have more than 1,500, actually over 1,600 registrations, and maybe we'll have even more attendees than that. The mix of attendees and participation has changed over time. We have now very broad industry participation, a lot of different companies contributing, sponsoring, and attending. And the kind of applications and the kind of problems that we look at have changed through the course of multiple GTCs. Today we will talk quite a bit about computer vision, using machines to recognize and analyze things, as well as machine learning, teaching computers to understand, analyze, and extract information from images and other data. As we have an explosion of imagery and other data that is being captured and uploaded to the internet, we have to figure out what to do with it, analyze it. It's just too much raw data for people to analyze, so we need to have the machines help us. Since its introduction, CUDA has really blossomed and expanded, and we think CUDA everywhere, and we need it. We want CUDA on every kind of device, from embedded devices in vehicles and other kind of objects, phones, tablets, computers, supercomputers, every place. We have over 500 million CUDA-enabled GPUs that have been shipped, a very large number of CUDA downloads, which indicates the size of the developer community. We teach CUDA in parallel programming courses worldwide. Probably by the end of this year, early next year, we'll be close to 1,000 university courses teaching CUDA, and that leads to new applications, new exciting ways of using GPU computing, academic papers, research, and real products, real technology that makes use of CUDA. I'll just highlight a few examples of things that have been done that we think are particularly interesting. There's a company called SU, I believe they're in Australia, that has been exploring using GPU computing to enhance the capability of drones for unmanned aerial vehicles. Onboard GPUs are used to do navigation and collision detection. So you can have more drones up in the air looking for forest fires and doing surveillance for people's safety without colliding with the other drones that are in the air at the same time. At the University of Illinois, on the Blue Waters supercomputer, there were over 3,000 GPUs applied to the problem of simulating the capsid of the HIV/AIDS virus to try and understand the infection mechanism and be able to potentially defeat it. If you can understand how the capsid works, you can prevent it from being allowed into the cells and infecting cells. That simulation involved simulating over 3 million atoms in the molecule. I think it's a truly amazing achievement. Another company, Hologic, is using GPU computing to do 3D reconstruction of imaging data for breast imaging to do a better job than simply using X-rays for identifying a disease or tumor tissue. So that this results in much lower radiation doses and much better quality detection and much better quality healthcare. The GPUs are changing people's lives in all these ways. Closer to home, work that's going on in Japan, Tokyo Institute of Technology. There's a project that is using parallel GPU computing to identify substrings or K-mers in DNA sequences to try and determine the frequency of particular patterns. And this can be done much more efficiently with GPUs and CUDA. At Waseda University, they're using GPUs to teach robots how to select appropriate behaviors. They use a deep neural network and GPUs to train the network and figure out parametric motions, how the robots should behave. Purdue University, here's a project where they use parallel finite element model simulation to simulate the deformation and fracture or tearing of soft biological tissue to simulate surgery and provide training haptic feedback for surgeons to be able to learn how to do surgery without actually cutting real flesh. So these are very exciting applications, and these are examples of GPUs really changing what we're able to do. One recent announcement at the International Supercomputing Conference a couple weeks ago shows the reach of GPU computing. Several companies have announced that they're going to build ARM64-based servers for high-performance computing, and this is really significant because traditionally other CPUs have been used as the core processors for high-performance computing, and ARM64 is a much more lightweight kind of CPU architecture, much more power efficient than some of the processors that have been used before. But by itself, ARM64 would not be sufficiently powerful as far as computing to really build a supercomputer. A combination of CUDA with GPU computing combined with ARM64 CPUs provides an excellent power-efficient substrate for building next generation of high-performance computing. It's certainly not the only way to build these, but is a new innovation, is a new approach to building high-efficiency, high-performance computers. Other approaches to power-efficient supercomputing, the Green 500 measures the most power-efficient implementations for supercomputers, and all of the top 15 winners in the last round that was announced have NVIDIA GPUs in them. In fact, they have Kepler architecture GPUs. And again, number one is very close to home, the Giovanni KFC supercomputer, which is at Tokyo Institute of Technology. I just found out yesterday that KFC stands for Kepler Fluid Cooling, not the Kentucky deep fried chicken that you might associate with KFC. But the name is appropriate because it is the processors are immersed in oil to manage the thermal cooling for the computer. So the processors run at a very reasonable, much lower temperature than in an air-cooled or water-cooled system, and so you get more power efficiency. I think it's a really great machine, and maybe the way to the future for supercomputing. We may see a lot more oil-cooled systems. So the other implication of Kepler, besides moving up the computing food chain into supercomputing, Kepler has also moved down into our mobile architecture. You may or may not know, historically, our mobile architecture, the Tegra family of processors, had a different graphics pipeline than our GPUs for desktop and high-performance computing and laptop. the progression of architectures for the desktop from Tesla to Fermi to Kepler and on to Maxwell is our fully capable, fully functional, that's all graphics, that's all computational graphics, supports CUDA. With the introduction of our Tegra K1 mobile processor, we now unified our architecture. So going forward, we'll be building a single graphics architecture which spans the full gamut from mobile and embedded architecture all the way up to HPC. And what that really means is that all the capabilities from programmable graphics, visual computing, all the way up to CUDA and programmable parallel computing are available from embedded architectures to be deployed and developed all the way up to very high end. So now I'd like to demonstrate this really awesome power of Tegra K1. If we can switch to the demo. Amazing quality of graphics for a mobile device. Let's take a little drive through here, explore the environment, see the nice quality reflections of the water at the damp floor, see the indirect lighting and special effects, the God rays in the background, the light shining through the atmosphere. So really this is virtually indistinguishable from the desktop gaming experience, truly capable. And this is all running on a Tegra K1 development platform running under Android. We pull up the Android menu here. So you can see it's fully integrated with Android. So it's very exciting. Thank you very much. Let's go back to the slides. Okay, so Tegra K1 allows a whole bunch of new experiences for handheld and embedded devices. Besides gaming, which I've just shown you, Tegra K1 was all over the recent Google I/O conference. I showed you the gaming, which is part of the new gaming environment on Android. We're also very involved with Android TV. Computer vision on a tablet, the Tango project where you can capture 3D information with a tablet. We're in Chromebooks. We're the first Android Auto platform, and we're also the first development platform for 64-bit ARM with Android L release. So we're really enabling a great breadth of GPU computing on Android everywhere in Google I/O. So it's a truly impressive platform, and we built a truly amazing development vehicle for it. Jetson TK1 is what we call the first mobile supercomputer for embedded systems. We have Tegra K1 on it, and all the other peripheral connectors, memory, and all the other pieces so that you can have a full, fully functional computer on board. So it's a mobile supercomputer. It has 192 CUDA cores. CUDA 6.5 offers support for ARM and development, a bunch of tools, SDKs, and libraries that allow you to develop applications on this platform. And this is 326 gigaflops on a very small mobile chip. It's really a tremendous achievement. And you can get hands-on experience with this here today, and it's also available in retail. You can order one. I don't know the Japanese price, but it's a very cost-effective, very excellent entry into GPU computing and development. Okay. So another topic I'd like to talk a little bit more about is machine learning. And machine learning is a pretty old branch of artificial intelligence, first explored maybe 50 years ago. And the idea is that computers can, on their own, learn from data, from information that you present to them. And the best way to be able to do this is unsupervised learning, where the computer program will go through a whole sequence of training data, for example, images, and figure out what can be recognized from it, figure out different classes of things that it can identify. So just like humans, we're born without the ability to identify and recognize specific kinds of objects or animals, but we learn over time as we experience our life. You want to have a computer program that's doing machine learning be trained on a set of images and learn to recognize a person or a dog or a cat very effectively. This is very hard to do, though. So this is we're at a very special time in the history of machine learning because there are a few trends that are converging, things that are happening at the same time. The first one is there's an explosion of data. I mentioned that earlier. Just a few years ago, there were approximately 300 million images being uploaded to the internet every day. And today, probably by the end of this year, there'll be close to 2 billion images uploaded per day to the internet. And all of this is just people's pictures. And they're unclassified. You don't know what's in those pictures. But you would like to be able to figure out, recognize faces, recognize people, like recognize objects. Like show me a bunch of pictures of cats, for example. There's also a study in deep neural networks, which is a approach for machine learning. And the growth of GPU computing, the explosion of parallel pervasive computing. The three of these things together are enabling a real explosion in machine learning. So a while back, Google Labs built a project called Google Brain out of 1,000 CPU servers, over 16,000 cores, spent quite a bit of money and quite a bit of power, over $5 million, to build a deep learning system that they were able to train over the course of many weeks to recognize a variety of features and images. So there's considerable excitement about just scaling up to this level and being able to do that. Sometime later, Stanford AI Lab was able to duplicate the performance in terms of recognition quality of Google Brain with a much smaller substrate. So 3 GPU accelerated servers, roughly the same number of cores in 12 GPUs, and about 1/150th of the power and much lower cost. So we really see machine learning becoming pervasive, getting much more broadly applicable. And another example of this is ImageNet, which is a very large collection of images that are commonly used as a baseline for machine learning training. There's a challenge that happens every year where people write their own programs to compete with other people who are trying to demonstrate that they can recognize features in image. And just last year, more than half of the teams competing in this effort were using GPUs. So you can really see that this leverage, this advantage of highly parallel computing is something you can't ignore. It's going to revolutionize machine learning. So you can see this by the fact that many large companies are using machine learning for production for real products. And there's a lot of important research going on in universities in this area, so the field is moving very, very rapidly. There's a very broad collection of use cases. I just mentioned the image classification, but pretty much any situation where you have a large volume of complex data and you want to extract some meaning from it, machine learning is going to be the way to proceed. It's the only way we can deal with that scale of data. So it's a very exciting development. Next, I'd like to have some presentation about enterprise virtualization, and I will step off the stage. Please welcome Mr. Mark Hamilton, who will talk about this topic.
Welcome, everyone. It really is amazing that we've come this far as the word in OP Video set. If you think about it, it was only 21 years ago that NVIDIA was founded in 1993. It was the first GPU in a PC on the desktop. And think back to 1993. There's been a lot of change since then. Unless you worked at CERN Labs in Switzerland, you probably had no idea in 1993 what the World Wide Web was. And unless you lived in Finland and worked for Nokia, you were still, if you had a cell phone at all, was an analog cell phone that only did voice. And of course, you had a GPU on the desktop. And David spoke about all the great things that have happened in graphics and in computation. So let's talk a little bit about the changes going on in enterprise virtualization. Enterprise virtualization 2.0, as we call it. Surprisingly, with all those changes in the last 21 years, enterprise virtualization is really focused on the server. It has left behind graphics. Slide-by-slide comparison. So on your left, you see one of our partners, Citrix Desktop. They're the world's leader in desktop virtualization. They're running an application. This is very similar to Google Maps. It's called ArcGlobe. And what you would expect the performance on the right, on a low-end laptop, when you virtualize in the data center using only software-based graphics, you get the very poor experience on the left. Again, users have not been happy with this, and not installed NVIDIA Virtual GPU in Grid technology was adopted by Citrix, was able to deliver a real graphics performance in a VDI or virtual enterprise experience. So a short video is nice. You can actually see that video on YouTube. But if you follow me on Twitter, I did promise this morning that I would make a special announcement. So we wanted to make sure that all of you when you left could not just see a video of graphics accelerated VDI. And I expect some of you may want to talk to Citrix, your hardware OEM, and actually start a trial in your own company of graphics accelerated VDI. But we wanted to make it even easier for you. And so as you would expect with enterprise virtualization 2.0, we took the NVIDIA Grid technology, and we put it in the public cloud. And starting this week, right here in Tokyo, you can sign up and get a graphics accelerated desktop for 24 hours. So rather than just talk about that, I'd like to invite up my first guest to give a quick demonstration. So please welcome Mr. Masaki Sawai, who's going to come up and give a demo of the Grid test run.
それでは実際にグリッドテストライブ見ていきたいと思います。グリッドテストライブに必要なパスタです。通常のパソコンと、皆さん、使いのパソコンとインターネット配信をしたんです。はい、グリッドテストライブを使うのは、3点で、まずは、ブラウザを開いていただいて、www.nvidia.co.jp/グリッドという数字をいただくと、グリッドテストライブのプレゼンにつながります。こちらで、テストドライブをお試しください。ボタンをクリックしていただくと、アカウントの登録画面に移ります。こちらで登録をお願いします。登録は無料となっております。登録が完了しますと、グリッドワークスペースというソフトウェアをダウンロードしてください。ダウンロードして PC にインストールします。以上でグリッドテストドライブを3準備が完了します。それで実際にグリッドワークスペースを起動しています。まずはですね、ログイン情報がございます。こちらはですね、登録で使用した情報を入れてください。いただくと、日本の皆様、配信にしてください。そしてサインインのボタンを押しますと、パブリッククラウド上でハートマシンが立ち上がり、デスクトップの準備が始まります。宿泊すると、このように、Windows の画面が出てきますが、こちらはですね、クラウド上で動く Windows のデスクトップでございます。こちらのデスクトップはですね、NVIDIA グリッドによって GPU アクセレーション、より感情となっております。そして、このグリッドテストドライブでは、デスクトップ上にですね、あらかじめデモ用のアイコンをしております。ダブルクリックしていただけば、手軽にグラフィックのですね、アプリケーションを体験していただくことが可能です。実際に見てみましょう。まずはですね、ウェブブラウザで、ウェブブラウザでの HTML タイプを全部でございます。GPU アクセレーションのウェブブラウザ上で、このように製品の表現可能となっております。はい、この試合というのも可能ですね。パネモデルを借ります。そうですね、こちらのグリッドテストドライブの環境ですけども、最初のチェックラッチャー、チェックラッチャーの編集を使うことができます。ですので、こちらのようにですね、ハイエンドのグラフィックを使ったアプリケーションも問題なく今できるようになっております。それも見てみましょう。 この写真のアプリケーションとして、シャドウのビューアーが一切搭載されております。こちらはですね、シムセンターのですね、シャドウのビューアーの画面でございます。こちらのですね、自由にマウスをタッチに出してに、シャドウモデルを最新に動かすことができて、両側しっかり正確に同じ今お分かりだと思います。もしですね、ソリッドはスピード率も同じですね、こちらのシャドウモデルをですね、このように自由に下げております。センクレブリットを使うことで、いつでもどこでも、そして安全にシャドウデータを活用していただこちらをテストで手軽に体験いただくことが可能となります。こちら、あらかじめ用意されたデータだけなく、そのデータに対してはですね、こちらの使い方内容ですとか、ですのでね、運動に効果を持ち出して、そのデータを取り出して、収益化が可能となります。このようにですね、ウッドテクノは PC とインターネット環境の違いがあれば、いつでもどこでですね、ブラックを使った発想ですとか、大変可能となります。この番組を行っておりますし、今、現在からお伝えがありますので、ぜひ皆様、そっちをお試しください。そっちに行っていただけると思います。ありがとうございます。Thank you.
Thank you. That was an amazing demo. And once again, it wasn't just a demo running on the laptop here or in a server behind the wall. That was, for the first time in 21 years, the full power of NVIDIA visual computing technology brought to you on a server in the cloud here in Japan, delivered to your desktop. And all of you can go, maybe not all at the same time, but go and sign up today. Less than 2 minutes to sign up. You can get your own graphics accelerated session. And if your company or your university or your organization decides they want to do an on-site trial, we have all of our partners in the room here today. Citrix, VMware, Cisco, HP, IBM, here to help you do that. The great thing about the cloud, we can not only bring you one GPU, but sometimes one GPU isn't enough. So with our iRay visual computing appliance, we can bring you tens of GPUs or even hundreds of GPUs to use in very advanced type of rendering. So now I'd like to welcome our second guest for Honda. Please welcome Mr. Daisuke Ide.
Hi, こんにちは。本田研究所の池と言います。今日は自動車のタイミングデザインの評価のために、ホンダが独自に開発をしていたツール、ソックスについてご紹介したいと思います。今この画面に出ているのはソックスというツールになります。ソックスは実装な見え方を再現するためのツールとして開発をしていました。そして今出ている例は、これ写真ではなくて、今現在リアルタイムで描画している結果になります。しかもここで使っている素材や環境的な情報は全て世界のものを取り込んでおりますので、実際に物を見た時の見え方を例えばヘッドライトの非常に難しい領域においても正確に再現することができます。じゃあ例えば、インテリアに行きましょうか。実はインテリアの計算というのは非常に光の計算が複雑になるので、膨大な計算量が必要となっていて、結果が正確にちょっと時間がかかります。今回は、実はその弊社で使っている 8GPU のワークステーションをこちらに持ち込んで、今こちらでこちらから今でも行っています。8GPU のこれぐらいですね。実は本社の弊社の中には 100GPU を2つのスラップをして運用しておりまして、そちらのこのような見ていただいている画面の大体25倍ぐらいのパフォーマンスで動かすことができ、そこのリアルタイムの動画環境というのを実現しております。また Excel に戻りますと、そしてこの特別にこいつは全てのタイム品のデータを中に持っています。そしてこいつは自由に画面を動かして好きなところで評価することができます。例えばこんな感じで回してみたり、通常ではなかなかお目にかかれないような見方なんかも自由に再現することができます。こっちもとても面白いんですが、実は面白いだけじゃなくて再現が非常に重要な機能です。例えば先ほどのヘッドライトの辺などは非常に複雑に機能部品が重なり合っていますけれども、こういった内包の機能部品を意識しながらスタイリングデザインを完結させていく、こういった業務においてこのような機能がとても有用になっております。このトップソリューツールはもちろん最新のレンダリング技術ですとか、それを高速で分回すNVIDIA の GPU テクノロジー、そういったものがあって設置しています。しかしそれではなくて、このツールというのは我々の強みである現場のスタイリングデザインが何を見て、一体どういうことを評価しているのか、一体実測で見るとどういうことなのか、そういったものを深掘りしていった結果、我々のツールであると確信しております。今回このようなデモの機会をいただきどうもありがとうございました。Thank you very much.
Thank you. Thank you. So another amazing demonstration of NVIDIA technology. So in a short period of time, we showed you how we've taken the GPU off of the desktop for graphics, finally enabled enterprises and in fact the cloud service providers to bring that back into the data center. So that's not the only place we're taking GPUs. You saw how the Honda car was designed on the outside and inside using GPUs. And next, I'd like to welcome Mr. Danny Shapiro, who's going to come up and talk about how we're putting NVIDIA-powered supercomputers inside the car. Welcome, Danny. So hi, everyone. It's wonderful to be here. Really enjoyed coming to Japan, Tokyo, and being able to tell you a little bit more about what we're doing in the automotive industry. NVIDIA actually has been working with car makers for over 15 years. Virtually every single car on the market today was created using NVIDIA GPU. The designers in their early concepts are using computer graphics, NVIDIA-powered workstations for styling and design. The engineers, as you saw from a CAD perspective, from a manufacturing perspective, they rely very heavily on visualization to be able to lay out all the thousands of components of the vehicle, to lay out the factory floors, and to model all this, again, using computer graphics and our GPU. In simulation, GPU compute is being used to do all types of work that usually would take days, weeks, or months and require millions of dollars. It can now be done virtually. So virtual crash test simulations, virtual wind tunnel simulations, virtual traction control studies can all be done interactively and iteratively to create better cars. We're also now moving GPUs, as you saw, into the cloud, but enabling the marketing and sales of cars as well. GPUs are able to do custom car configurators that can run on your tablet, being connected to the cloud, or do virtual showrooms, as Audi is doing in their Audi cities around the world. Again, a virtual showroom that lets you design and customize your car. A lot of advanced technology, as you see, is being used in the design, manufacturing, production, and selling of cars. But now we're really excited to be able to take this technology and actually bring it into the vehicle itself. So NVIDIA, as you know, is well known as a computer company for creating a wide range of different types of products, from phones and tablets at the low end to laptops and desktop computers to servers and to cloud, high-performance computing, all based on a scalable architecture now. What we're doing is leveraging elements of each of these platforms and creating a computer platform for the car itself.
So the Tegra processor, as you know, is a mobile computer. Now it's actually a mobile supercomputer. What we've done now is built an automotive-grade module. That's the Tegra Visual Computing Module. This is what's going in the cars. Essentially, this is a computer that runs an operating system. It can run Android, it can run Windows, it can run QNX, and you need open source code for automotive applications. This computer then has a lot of software that NVIDIA creates as well as our automotive partners work on together. But the benefit of this module is that much like your PC that you can upgrade over many years, this module is something that can easily be updated in the vehicle. The next video will show you what we've done working with Audi. This is their MID system, or their modular infotainment platform. What you can see inside is that Tegra Visual Computing Module. This enables Audi and other customers we're working with, BMW, Tesla, Motors, and others, to create these systems that have a lifespan that can be extended through software updates, but also potentially by updating the hardware. In addition, since the automotive industry tracks its life cycles much longer time frame than consumer electronics, the strategy gives automakers the ability to more rapidly increase the frequency with which they update their technology. Essentially, each model year, Audi is able to introduce a new technology platform that has greater and greater capabilities. The car you saw out in front, the Audi S3, features this new system, an advanced infotainment system. If we go back to the slides, we can see sort of the progression in this case, what Audi is doing in terms of applying multiple generations of Tegra. The infotainment system was the first step, but now as we develop more capable processors, advanced SoCs in our Tegra line, it's being leveraged for more and more computing inside the vehicle. The TT is a new sports car from Audi coming out next year that will feature an all-digital instrument cluster. This will be powered by Tegra 3. They've also introduced a very complex and sophisticated rear seat entertainment system that will be based on Tegra 4. This will be the world's first automotive-grade tablet designed to dock in the vehicle, communicate with the vehicle, but also be able to take it out and use it as a normal tablet. And then the Tegra K1, as was announced at CES, will be used by Audi in the self-driving and piloted vehicle. Again, a lot of different applications, all based on the same Tegra architecture family. As we go back and look at now the state-of-the-art in terms of graphics inside the car, NVIDIA is uniquely positioned to bring all the wonderful graphics research that we've done across all the different industries and types of things we'll hear about later today, and actually concentrate it and bring it into the vehicle to give the drivers and passengers a much better experience than they've ever had before. On one side, you'll see the virtual cockpit, the instrument cluster from the TT, which gets fully dynamic, can be personalized, customized as the driver wants to see things, but also changes for a context-aware situation. When you don't need a big speedometer or you don't need a tachometer, those can shrink down and display navigation, for example. On the right side is the Tesla Model S. It in fact has two of the Tegra Visual Computing modules, one driving an all-digital instrument cluster, and the other driving a 17-inch touchscreen. Tesla has done something that no other car company has done, and they essentially removed all the buttons, switches, and knobs, and replaced it with a touchscreen that again enables the driver and the passengers to access a lot of different information and customize their vehicle experience. In addition, being a connected car, the system can be updated over the air, much like your phone or tablet. So we're seeing the automotive industry, along with NVIDIA as a technology partner, really able to mirror trends in the consumer electronics space. From a graphics perspective, though, what we want to do is really leverage so much of the wonderful research and development we've done, along with you, to bring these capabilities inside the vehicle itself. Recently, we introduced a technology called material definition language, and what this is a very advanced way of rendering, not just doing basic OpenGL, but instead using the compute horsepower of our GPU to actually simulate how light behaves in the real world. Many different types of materials are comprising objects that we design, build, and buy today. What we wanted to be able to do was render how these different types of materials look. On the left side, you can see an example of how car paint is actually created. It's not just a single application of paint, but actually many layers. And so what we do is we render a base layer and how light would behave when it interacts with that base layer. In other coatings, there might be metallic flakes, there might be a gloss coat or two. And so we're actually simulating how photons bounce around in the atmosphere, how they react to the actual materials. And as a result, on the right side, you can see how we can render a whole range of different materials. Now, this is something that goes on all the time in the world of visual effects for movies, or even the beautiful renderings of cars that we do when we're trying to create a photorealistic picture. What we want to do now, and we are demonstrating, is the ability to bring that kind of visualization inside the vehicle and create a much richer experience for the driver and passengers. So this next video shows an example of a three-dimensional object, in this case an instrument cluster, being rendered with this technology, the material definition language. And here I've rotated to show you that it's actually a three-dimensional object. We can do very high resolution rendering, high frame rates, so you get very smooth animation of the needles, and then we can actually change the kinds of materials that are inside that vehicle, render something that's chrome maybe, or titanium, or carbon fiber. We switch to the next video, it'll show a clip of a user interface that potentially you could use on your phone or tablet to actually customize your own car. And here you can select, do you want a powder-coated material? Do you want some form of metal brushed or hammered? Do you want it to be copper? Do you want it to be platinum? The list just goes on and on. But we see the trend as people today customize their mobile devices, their phones, their tablets. The desire to be able to personalize your vehicle and have a unique look and feel will be very popular. Let's switch back to the slides now, and we'll talk about how, again, advances in supercomputing are really affecting the driving experience. Our goal is to make car rides more enjoyable, but even more important than that is to make them safer. Our technology, along with all the other sensors that are being put into vehicles, are going to reduce the number of accidents and fatalities on the road today. Now, it's quite astounding. There's over 1 million people killed worldwide every year in car crashes. In the United States, that number is about 34,000 people a year die. I was doing research, the number actually is very impressive for Japan. It's less than 5,000 people die annually. That's still 5,000 people. Ironically, part of this research unveiled that every year about 14,000 people in Japan die in the bathtub. So I'm not sure what's going on in the bathtub, but maybe that's a topic for another GTC and a problem we can try to solve. But 5,000 people a year in Japan is still way too many. What we want to do is use computer vision, use what we call sensor fusion, the ability to bring a lot of data in, analyze it, and reduce the number of traffic accidents and fatalities. The types of features that we're starting to see on vehicles now based on these systems include pedestrian detection, blind spot monitoring, lane control systems, cruise control that actually adapts based on what's in front of the car. What I'd like to do is show you an example of a computer vision-based system that we've been developing along with the partner named Shanti. Let's roll the next video. And what we can see here is the output from a front-facing camera being fed into one of our Jetson development kits. And what we're doing is analyzing all the frames of video, doing computer vision, basically detecting objects, tracking those objects, and then we can calculate what is the speed of our vehicle relative to the other object, what is the distance from our vehicle to that object, where are the lane markings, what are the street signs? And we can basically then become a brain that is the co-pilot to the driver. We can actually figure out what's going on around the car and alert the driver or potentially control the vehicle to avoid a potential hazardous situation. Let's go to the next slide. There's a huge amount of computation going on here. Many layers, and this is part of the VisionWorks toolkit. Again, CUDA is enabling computer vision to operate in real time here. Essentially, what we're doing is 3D graphics in reverse. We're taking data, in this case video, that's two-dimensional data coming in, and we have successive frames. So we can run different algorithms like structure from motion, for example, where we're able to detect what's moving and also get a sense of depth. So we can detect features in these scenes. We can then track them using our machine learning capabilities, understand what those objects are, and then actually build a three-dimensional scene of what these sensors are taking in. So the next video shows something that we demonstrated with Audi. And in this case here, what you're seeing is a side-facing camera as the car drives by, is looking for a place to park. What the camera senses, again, is just video. What the GPU is then doing is interpreting that video, creating a sense of notion of what is near, what is far, what is an object, what is not, and building these 3D fences. Then when it detects an opening, it's able to then sense that and will signal a place to park has been found. Again, this is all great stuff. It's all working in the labs. We have Nissan announcing autonomous vehicles. We have BMW, Audi, and many others really working on this. What we're really excited to be able to discuss with you today, though, is something that Audi showcased initially at CES, demonstrated at the last GTC that we hosted in San Jose, and now we'll be going into series production. This is something that the code name is GFAS, and what it is, again, is a piloted driving system. In the past, it required 4 large computers in the trunk to be able to process all the sensor data on the coming into the vehicle. What the system would do, though, is be able to detect other vehicles, maybe on the highway, and there's a traffic jam. The driver can turn on traffic jam assist. The car will then stay in the lane and maintain a safe distance to the car in front. So essentially, it's driving itself. The driver can take their hands off the wheels, take their feet off the pedals, and not have to worry. Then when the traffic dissipates, the system turns control back over to the driver, and they take over. Another mode that is very exciting of how this will be implemented is in self-parking, where the driver can actually get out of the car, press a button on the key fob, and the car will go into a parking lot, find an open spot, and park itself. And then when you're done, say you're leaving a conference, you press a button on the key fob, and the car's going to come out of the parking lot and pick you up where you left off. Now, the image on the left is a practical. But with Tegra K1 now, Audi is going to market with a system that will fit in the trunk of the vehicle, that will again enable the traffic jam assist, self-driving, as well as the self-parking. So there's a lot of great advancements going on today. The GPU is at the forefront of automotive. Looks like my car's out front. Time to go. Thank you very much. I'd like to please welcome back David Kirk. Thank you very much, Jenny. That was really exciting stuff. I can't wait for my car to do all those things for me. So now I'm going to talk about the future of CPU technology. I was talking about the future because it hasn't happened yet, so we can imagine all the things that are possible. But I think one of the best ways to talk about the future is to start with the limitations of the present. Aoki-san at Tokyo Institute of Technology has done a lot of really interesting work with GPU computing, and it's particular work that I have the slide here for. He's analyzing performance with multiple GPUs to solve a computational fluid dynamics problem for weather prediction. And as usual, the work that he's done, he has a really deep understanding of what's going on inside the machine while he's trying to do his computation. So some of the problems that he's seeing are represent bottlenecks in the system. In a modern PC architecture computer, there's some parts of the system that limit data movement and limit what you're able to achieve. The PCI Express connection between the CPU and the GPU is one such limitation. The memory capacity and memory bandwidth, particularly CPU bandwidth and GPU capacity, limit the amount of data that can be stored and the amount of data that can be shared between the CPU and the GPU. And what you see is, as you're trying to solve a problem, and as you're scaling up the problem size, where you have more and more computation to do, and you have more and more data to move around, these bottlenecks are beginning to limit your ability to effectively capitalize on the computational capability that is built into the chips. So these are problems that we'd like to try to go solve. So just looking at this in schematic form, the biggest limiter is the PCI Express bandwidth, which is very small, 16 gigabytes per second. CPU memory bandwidth is also relatively small. GPU memory bandwidth is very high, but we would still like it to be higher. We can always use more bandwidth. And the trade-off is typically CPU memory is large with low bandwidth, GPU memory is smaller with higher bandwidth, and communication between them is the slowest of all. So when you have